Okay, I'm going to use an example Olympiad question taken from, I think it was 1991, but I'm not entirely sure. Given the problem, given real numbers, real positive numbers, A1, A2 up to AN, and B1 up to Bn, with sigma AI equals sigma Bi, so the sums match. Given this lot, prove that A1 squared over A1 plus B1 plus A2 squared over nope, that's A2 plus B2 plus dot 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 plus AN squared over AN plus BN is greater than or equal to a half sigma AI. I'll just write that out a bit more neatly. Sigma AI, which is of course the same thing as greater than or equal to a half sigma BI, because this condition is the same here. So how on earth do we do this? It's easy to get intimidated when you see questions like this, but I want to look at this condition, AI equals sigma BI. There's obviously some symmetry between the A's and the B's. There's a symmetry here which is in the condition but not in the actual inequality here. And I want to get that back. I want to get that symmetry back. And how am I going to do that? Well, what I'm going to do is I'm going to call X equal sigma AI squared over AI plus BI. This is all I equals 1 to n. And I've got to show that X is greater than or equal to a half sigma AI. Well, to get the symmetry back, of course, I'm going to consider Y, which is the sum over the same things of BI squared over AI plus BI. Just by swapping the identities over, swapping A for B. Actually, I'm going to put in brackets what I really meant to write, which is BI plus AI. If I really did swap over A and B, I'd write it like this, with BA and AI, with B plus A on the bottom, not A plus B. But of course, it's the same thing on the bottom. I can swap the A plus B equals B plus I. And of course, writing it out this way makes it clear that the denominator of Y, the terms in Y, equals the denominator of the terms of X. So now I'm going to consider X plus Y, which equals sigma AI squared plus BI squared over AI plus BI. I'll write that out in slightly more long-handed notation. A1 squared plus B1 squared over A1 plus B1 plus dot 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 plus AN squared plus BN squared over AN plus BN. Now we'll be looking at the arithmetic mean, quadratic mean inequality, and one of the things that it shows is that x squared plus y squared is greater than or equal to a half x plus y all squared. This is just a restatement of the arithmetic quadratic mean inequality. But of course I'm writing it in this rather different way because I'm going to apply it to these guys here. So each term, x plus y, is greater than or equal to, well, I'll write it out term by term. It's going to be a half a1 plus b1 squared over a1 plus b1 from this term here, plus dot dot dot, plus a half an plus bn squared over an plus bn. And of course everything cancels out because a's and b's are strictly positive. Equals a half, I may as well take the half out, a1 plus b1 because I've got a squared and a linear term, plus dot 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 plus an plus bn, close curly brackets, equals a half sigma ai plus a half sigma bi. X plus y, get rid of that, is greater than or equal to these guys here. So it looks like we've proved it, but we haven't. We haven't proved it because it could well be that x is really, really massive. X and y could be very different size, and we're only interested in this one. We're not interested in this one. You'll remember from the upper sheet, the understand, plan, persevere, execute, review sheet for Olympiad questions, that we're introducing an auxiliary element, but it's very easy to forget when you're introducing an auxiliary element, such as y, that you're not really interested in it, and you've got to remember to get rid of it somehow. So we were sort of halfway there. I guess the other way to do it is to consider x minus y, which equals, well, let's see what it equals. Well, let's just bung it in. It's a1 squared minus b1 squared over a1 plus b1. See, this looks easier already, dot dot dot, plus an squared minus bn squared over an plus bn equals a1 plus b1, a1 minus b1, difference of two squares, a1 plus b1, and of course it's going to cancel, plus an minus bn, sorry, that's a plus, an minus bn over an plus bn. And of course, oops, all the summations cancel. All the a plus b terms cancel. Equals sigma ai minus sigma bi equals 0. Ho ho. So that tells us x minus y equals 0. So that tells us that x equals y. And now we've done it. Because here we know that x plus y is greater than, I think it was greater, yep, greater than or equal to a half sigma a plus a half sigma b, which equals sigma a. And therefore x is greater than or equal to a half sigma a, because 2x, because x equals y. So QED. Upper. Understand, plan, persevere, execute and review. Let's review. We're given this rather peculiar thing to prove here. a1 squared over a1 plus b1, and it's very easy, and I know because I've struggled with this problem for quite a long time myself. It's very easy to get sort of sidetracked into thinking, oh look, it's a1 times a1 over a1 plus b1, which is less than or equal to a1. Hang on a minute, we're looking for the inequality the other way. It's easy to get sidetracked by looking at this kind of issue here. Really the key observation is the symmetry between A and B, which I've been trying, which is lost. You've lost the symmetry between A and B in this formulation here, and I want to get that symmetry, which is given by the condition here, back. I want to get that symmetry back, and once you realise you've got to get that symmetry back, the whole thing just falls into place. Okay, I'm going to stop there.